Good evening, dear student, and welcome to this other edition of our functional analysis class, the 13th edition. Today, we are going to tackle the notion of Banach spaces. Banach. Of course, it's a German name. Some would say Banach, as if it's say, but it's a Banach. Banach space or Banach. If you find it difficult to call or to pronounce, you say Banach. But it's Banach. Banach spaces. So that's what we are going to see. What is a Banach? A Banach space. A Banach space is it's a complete matrix space. A complete norm matrix space. It's better to say norm. Norm. A complete norm space. It's true that a norm space is a matrix space, but a matrix space is not necessarily a norm space. I hope you are already familiar to this. If not, try to get familiar with this notion. A matrix space, because we saw that a matrix space that is, when you say a matrix space, it means you have a metric, a distance. But if you have a distance, that distance does not necessarily define a norm. But if you have a norm, from the norm you can define a distance. That's why norm space is a matrix space. But a matrix space is not necessarily a norm space. In general, it's not true. But now, if you are given a distance, or if you define a distance, to see if that distance can define a norm, you check if that distance is homogeneous, first thing, homogeneous, and invariant by translation. If your distance satisfies these two conditions, if your distance is homogeneous and invariant by translation, therefore, it defines also a norm. So it can define a norm. And we know how to define the associated norm, right? You just take the distance from 0 to a point. Obviously, you have to be in a vector space. If it's just a simple set, which is not a vector space, forget about it. It has to be a vector space. If it's a vector space, then you check if that distance is homogeneous and invariant by translation. If the two are, then you take the distance from 0 to an arbitrary vector that will define a norm. Right, so from that you get your norm space. Now, I'm going back to the definition of a Banach space, because for the Banach space, I have to make sure that it's a vector space with a norm. If I have a vector space with a norm, and if that norm is complete, therefore, it's what we call a Banach space. And what is a complete norm space? It is a norm space in which every Cauchy sequence is convergent. Every Cauchy sequence is convergent. I didn't say Cauchy. Of course, some will say Cauchy. The name is Cauchy. Normally, if I want to pronounce originally, its original name, because people will try to make it English. If you are in an English country, if you are in Germany, they will try to make it a German name. But originally, the name is Cauchy. Cauchy. She, as if it is SH, not CH. Cauchy. Cauchy. Because of, if you try to really say Cauchy, that is Cauchy. So to remember how to pronounce it exactly, it is C-O-S-H-I. Cauchy. That is exactly the way it's supposed to be pronounced. Okay, so that's the definition. And once you understand the definition, the rest is just putting it into mathematical statement. Okay, now let us go straight to the definition and some examples, because that is the most important thing. Banach space is a complete, you see now, you have a complete, so you see complete norm. You have norm, right? Of course, when you say already norm, it has to be linear space, right? Because a norm is only defined as a linear space. Why? Because you'll be adding two elements. So it has to be a linear, because if you add two elements, the element has to be, I mean, the space has to be stable by addition and scalar multiplication. So it has to be a linear space. Complete norm space. Full stop. It's a Banach space. That is a space in which every Cauchy sequence converges. Every. That's all. Of course, converge with respect to the topology. Topology means with the norm, right? Because we saw that with the norm, we have a topology. Right. Why do we have a topology? Because a norm, from the norm, I can define a ball, right? I can define a ball. And we know that if I have a metric space, because the norm space is a metric space, from that metric space, I can define the ball that generates the topology, right? We saw it, so I refer you back to how we defined the underlying topology from a metric space. That's exactly what you do. So you take that topology, and then you can talk about open set, convergent sequence, and all that. Okay, now, I'm sure, yeah, obviously, in real analysis, when n is equal to 1, at least, and this norm is reduced to absolute value, right? It's absolute value. Why? Why? Because if you take n equal to 1 and p equal to 1, for instance, we know that in R1, right, because that's a 1, in R1, in R, which is R1, let me put it like that, right? If I take the one norm, right? We know that the one norm is this one, summation, let me use k, from 1 to n, absolute value of xi, because it has to be 1 and then to the 1. Anyway, let me, if I take p equal to 1, this is what with the p norm, this is what we have. 1 by p, p is 1. Now, because n is equal to 1, we just have x1, which is in fact x, right? Because there's only one component. That's absolute value of x1, which is absolute value of x. So that is the absolute value in R. So you can see that with this example, takes you back to the fact that in R, as a norm space, or because matrix and norm space here will coincide. So in R, with the norm, which is reduced to the absolute value, right? This is a norm space, obviously, right? So this one, you saw that this is a Banach space. Anyway, here in real analysis, you saw that every Cauchy sequence in R converges. So R, I'm sure you saw that R with the norm is a complete metric space. So with a new definition, I just said that it's a Banach space. So this is real analysis. Real analysis. You saw this. Now, as a homework, I encourage you to do this with Rn. Instead of stopping there, just use n. That's n component. You can still keep this with a 1 norm. You can even move to an arbitrary p, 1 by p. You can take the 2 norm with 2 here, but Rn, right? You can use 1 norm or 2 norm with Rn. You can even go to the arbitrary p norm, where p is less than infinity, because when it's infinity, you can change that to the supremum. You can do all of that. You can try, and you can try that. I don't know if I uploaded the, let me check quickly for this case of Rn. I'm sure I have it somewhere. If I find it, what I would do, I would just upload it for you to read. Okay, I'm checking one of the notes here. This one is about metric spaces. I want to find out if what I want you to learn is there. Complete spaces. Okay, let me check that one. Complete definition is there. A metric space is called complete if all Cauchy sequences converge. That's for metric. Now, instead of a metric, you have a norm. Space becomes a Banach space. Banach's fixed point theorem. Okay, compact space. Will be compact. Okay. Extreme value. Compact set, and that's the end. This is not what, even though it's already good, this one on metric spaces is already good, but unfortunately, unfortunately, Okay, I can read here in another note. Every Cauchy sequence in R converges. That's what we did in real analysis. Okay, now you have example. Yeah, I think I can send you this one. It's 20 pages, but you can read from page 4. Let's say from page 3. Yeah, because there they define what's a Cauchy sequence, and then after that, every Cauchy sequence in R converges. And then on page 5, definition, a matrix X is complete if every Cauchy sequence of point in X converges in X. And then the example of Rn is given. Rn is a complete matrix space. And then, okay, they say let each coordinate. Yeah, they give they give the detail of the proof, and then they take lowercase lp. They give yeah, and they give the step exactly what you need to do. Maybe they did not write the proof step by step. Then now it's up to you to write it properly in detail. I think what is even given here is enough. This will be your second. Okay, what I will ask you to do for your second assignment. You read this. I will send this to you. You read both for Rn and for LP, lowercase LP. They gave the steps. They almost explain everything. Yeah, almost. Yeah, I think it's a really. But what I want you to do now is to write the detail for yourself. Not to plagiarize, read to understand, but put it in your own words. All the steps here. Yeah, because this will really allow you to understand the steps. That's why I want you to do that as an assignment. But now what you'll be doing, it will no longer be for a metric, because here it's for a metric space. But you convert this not to a metric space, but to a Banach space. So this is just for you to see the steps. Yeah. Okay. Yeah, no, that's good. I think that this one is really, it will do the job. So what I will do now, and you have even extra compact set, everything is even there. It's really more detailed. This is a gift. This is a gift. I'm giving this to you. Take your time to read. It will pay off. Right? This will summarize a lot of knowledge you need to have about what we covered so far. Extra. And this is even for economic student. That's surprising that in economics you can do this type of mathematics. You see here in the references, foundation of mathematical economics, mathematics for economists, and they are doing these things. That a lot of so-called yeah, it's economics 5 to 6. So-called people having, or who are having, because I wanted to say who are aspiring to have, or who are prospective bachelor degree student. People taking this functional analysis, they already have a first degree. Now see what is being taught to students in economic, University of British Columbia. That's what a lot of people with honors degree even cannot do. Because what I can see is really impressive. Okay, I will let me do it even now. Let me do it now. Copy. If you play, you'll find some economics student will be teaching you these things in topology and on the line, because I can see it. Maybe not from from Namibia, but from other part of the world. I can see here. Maybe to avoid talking too much, let me share the screen, because I can see that you are not. I've been talking, but you don't have access to that. This is what I'm talking about. Metric spaces, topology, and continuity. This is a 2016 note from University of British Columbia, Economics 5 to 6. Okay. So in this economic class, they are covering this sequences and limits. And I think that for you, please read just 20 pages. Try to read everything. There are things that you will not understand, obviously. But the most important thing here for you, like here you can see, any norm space is a metric space. And they show you how you can get the distance from the metric. That we did this already. Right. And now they give you some example, like in Rn, they give you that. A sequence in a metric space converges if, well, then you have the definition there. They give you an example here. Some details that we don't have time to go through, you have them here. See, with example, it's really, you will appreciate, and you will give me a Vambo chicken for sure as a gift. In return of this gift. Many concepts. If you go through this, there are many things that you will understand. Please take your time to read this carefully. Carefully. This is for economic student, right? And there are many concepts that you will understand here. Cauchy sequences. A matrix space is complete if every Cauchy sequence of point in X converges in X. Right. And these are the examples I was talking about in Rn. They try to explain here. So I'm asking you to do this in Rn using the p-norm. Right? You can, because here they give directives. Because what is the idea actually? What is the idea? And I will explain it. Let me first, here in Rn is even easy because from Rn you go back to R. That is the idea. Rn is like, it's not yet heaven, right? It is somewhere between heaven and earth, an intermediate space somewhere there. So we are in Rn there. Let's say it's like a skyscraper. Maybe you are on the 100th floor somewhere there. Or you are in the plane. That is your Rn. But you are not yet in heaven, you are just there, somewhere in the air. But you can still be in contact with the human being. And then when you land in the real world, which is R. No, this is just an analogy because actually, whether I'm here on Earth or in the space, it's still Rn, right? Still Rn or R3 if you want, 3 dimension. But by analogy, I will use the ground or our not the universe, but the surface of the earth, like R, because here you are in the real world where you live. Yeah? That is our R, because we know everything about R. That is our real life here. Now, if you are in a skyscraper, 100 floor, 200 floor, whatsoever, there, or you are in the plane, it's like a level above our R, which is I can call Rn. So what they explain here, because we know already the property in R, from Rn, it takes you to R. That's what it's doing here. And then we use the fact that R is complete, because you don't need to prove it again. You did it in real analysis. So you use that information, and that's what you'll be doing for any other space. Now, when I dive into functional analysis and we define spaces, that is, which is not Rn, which is not R. I mean, when I say Rn, I mean n equal to R, 1 is R. So any other space, it will be as if we are in heaven. In heaven. Not the heaven, because you have many heaven, you have the third heaven. Let's say you are in the first heaven. Those are those spaces. Now you have to come back on earth, right? Like an angel who is sent on earth to give a message or something like that. You see, so you are there, and then you go back to earth, and then you go back to the space. That is exactly the idea behind. This is an analogy that I'm taking for you to understand. So when you are there, or in a Banach space, abstract space, you have to come back to earth to use what you know, and then you go back. You see, that is exactly the idea. I am in Rn, I come back to R, I use my result, go back to Rn, because I want to prove it in Rn. If I am in an abstract space, abstract that is infinite dimensional space, I manipulate in such a way that I come back to the real world, which is our R, for instance. And in R, I use the fact that R is complete, or it's a Banach space. Then I use that result, I construct, and I go back to the space where I want to prove the property. Okay, that is it. So you can see here as well, in LP, if you go into the detail, you see exactly what is happening. You see that LP here has nothing to do. Obviously, when I say it has nothing to do, but you can see that each x of I is in R here. You see, that's the connection. This one is in R. So you leave this LP, and you have to dive into R to use this information that a Cauchy sequence in R is complete. You see here, R is complete. You do the same thing with lowercase l here. So because when you write Cauchy sequence with this norm, in the LP norm, we are here. But each of the component, you have to make sure that you extract one of these components, because there are many components. You see that when you write the definition with this, you'll be able to. And how do you do that? This is the thing. You see, because this norm, this one, which is this norm, is greater than this one. Here we are already in Rn. Why? Because if you take the p root of this one, right? You see, when you take the p root, it gives you this. Now you see that if you take less than epsilon here for the Cauchy sequence, it will also indicate that this one is less than epsilon. That in here already in R. So you move from LP to R with this inequality. And you use the result in R to indicate that this one will converge. And then you reconstruct back to go back into LP. That's exactly what I'm talking about. So please take time to read this properly, and you'll be able to do that for any other space. Because the way an arbitrary space will be defined, you see where you can extract, because there will always be a connection with R. In a certain manner, you have to find it. I take the case of integral. When you write integral, let me take the case of an integral. If I want to use the case of an integral, okay, this is something else. If I want to use the case of an integral, for instance, let's say LP. With LP, the norm, oh, sorry. If I write, for instance, Cauchy sequence in terms of LP, right? Now this LP is no longer this capital LP, this one. If I'm using this, you see that the integral will be this, like that. Obviously, let's say I put R somewhere here. Let me put X just to generalize. The integral here. And now here we have absolute value of f mx minus f nx, absolute value to the power of p, like this, dx. Okay, I will continue here, dx, like that. And then I will close, and I will take the 1/5, right, like this. That is it. Now you can see that if I have something, let's say this less than epsilon, when I will raise this, right, if I take this less than epsilon, to write that as a Cauchy sequence, I write whatsoever definition I reach here, I say less than epsilon. Now, if you raise this to the power of p, you see that this to the power of p will be less than epsilon to the p. But now, what is this? This to the p will be this integral, will be this part. Integral dx. And this is this, and then you will write that is less than epsilon to the p, right? Whatsoever the definition of Cauchy sequence then implies, or then you are here. Then you are here. Now, don't forget, there is something that we wrote here the other time. Because from here, but you can see that this part is in R. Now the question is, how do I make sure that I can dive into R? If I can get rid of this integral, then that will be possible. But how can I get rid of that integral? If you recall what we did when we compared the one norm, was it the one norm? We compared something here last time. Was it the one norm and the infinity norm? Anyway, let me quickly check on the previous slide because I remember we did something, but let me see if that one will work. If it works, okay, it was a 2 norm less than the infinity norm. Okay, that one will not work directly because I have to write that it's greater than. Okay, now for the LP, because we are, some will be Banach, some will not be. So P has to be between 1 and has to be finite. We didn't cover that because you do that when you go through the LP spaces. But can we do it directly here like that? It will not be obvious directly, but we can still do it. Okay, so Okay, so we have, okay, you can, oh yeah, that one is between the infinity norm and the 2 norm. Because if you show that the infinity norm is a Cauchy sequence, you use that directly to show that L2 is also a Cauchy sequence directly. It's a Banach space, sorry. Yeah, you can use that because if you recall what we said, that if you have a stronger norm, something that converges for the stronger will imply in the weaker, right? Yeah, that's what you can use that. Okay, but anyway, so what I was trying to say, maybe this one will not necessarily work, but if you can move from here and just extract this and prove it, then you go back to R and come back up. But we will look at this when possible. I will find a time to do that. But with the LP, it will be more complicated, right? It will be more complicated with the LP. That one's a special case. But instead of the LP, let's just look at the case where you have continuous function. For continuous function, if you remember with continuous function, we saw that you can, yeah, you can still use this integral. But now that case, instead of having x here, you have a closed interval, right? We will do that. We will do that. Okay, so now here is open set. So please go through this and try to read. I'm giving you time to read this by tomorrow. Please read this by tomorrow because I want to release by tomorrow another one on these things I'm talking about. But before I do that, I want you to first assimilate this because if I come and add everything at the same time, you'll be overwhelmed. Please, I will stop here for today. I gave you the definition and I'm asking you to read this note. I said 20 pages. You don't need to read all the 20 pages. You just need to read from page 1 to 6. Enough. 6 pages. You can see here, this is page 6. So you stop here. Of course, when I say stop here, it's for the Banach. For Banach, you stop here. Stop here for Banach. Open set, you can read to enrich your knowledge. But for Banach, stop here for Banach. That is for tomorrow. So you have 6 pages to read for tonight. Stop here for Banach spaces. So you have a total of 6 pages. 6 pages to read. So read and make sure that you understand. Okay, so once you understand that, please put it in writing because this will be part of your second assignment. I will add, you will do this one, and I'll add an extra exercise, and this will constitute your second assignment. That if you can really understand this, it'll be wonderful. You will learn something. Okay, let me upload this on the platform. Okay, okay. The other one I was talking about is this one, when this is a continuous function with the infinity norm. This is the proof. Please read the proof. I will not go through that now, but try to read the proof with the previous note that I will upload on the platform. Make sure that you understand. make sure that you understand and you can redo that without looking. Try to practice. Make sure you can practice and write this properly, because the steps that you will take to do this, that will be similar to what you'll be doing if you are given an abstract, something that you have never seen. Because the construction will be similar, not exactly the same, but the similar. It will inspire you to construct for an arbitrary order space. So that's why it's better to try to understand, to redo it yourself. Write without looking. If you are stuck, go and read, try to understand, and you should be able, it should become like a reflex, right? That you'll be writing, doing stuff on your own, so that tomorrow, even if you don't have, you know already what are the steps. Try to first, if I can use the word, memorize the steps. Once you memorize the steps, later on you understand that I need to do this first, I need to do this first, and it will be exactly the same steps. Now the next thing is, how do I write it down mathematically and properly through reasoning? So once you succeed to do that, finish. The concept will be there. And that's what I want you to try to build. So please go through this, but I will record another video where I will go step by step through this. And this should be all. Huh? So let me upload this on the platform. Okay, so I've just posted it, so it's there. All right. I will stop here. I'll stop here. Okay, so I wish you all the best. Good reading and enjoy. Have a happy mathematics night because we're meeting tomorrow. Yeah, listen, tomorrow by tomorrow. Please, 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 I beg you, take time to read. It will be beneficial to you and you will pay. Bye-bye.